Take a moment before we go any further. Look around you. Your room, your living space, the street outside your window. Everything you see feels solid, real, dense with matter. Now imagine someone proves to you, mathematically, that at a scale your brain simply refuses to accept. Almost none of that is actually there. Not as a metaphor, not as philosophy. Literally. An emptiness so vast that our entire galaxy, the Milky Way, its 200 to 400 billion stars, its planets, its oceans, you and me, we drift inside it like a single speck of dust floating in the middle of an empty room the size of a continent. And here's what has been turning my mind inside out ever since I went deep into this subject. This isn't speculation. It isn't a fringe theory. There are equations, there are maps, there are data sets from some of the most powerful telescopes humanity has ever built. And all of it points to the same conclusion. We are inside something we don't even have a proper name for yet. So let's start with the obvious question, because it's a fair one. If we're sitting inside a gigantic void, why can't we see it? Why is it that every time we point a telescope anywhere in the sky, we see stars, galaxies, clusters, matter everywhere? This is where things get interesting. And this is also where most people make a fundamental mistake about perspective. What we call the observable universe is a bubble roughly 93 billion light-years across. That number is incomprehensibly large. But inside that bubble, matter is not spread out evenly, not even close. The universe looks more like a cosmic sponge or a web of unimaginable scale. Astronomers call it the large-scale structure of the universe, the cosmic web. Within that web there are filaments, long threads of matter stretching hundreds of millions of light-years, where thousands of galaxies cluster together like beads on a string. And between those filaments, there are voids, supervoids, regions where almost nothing happens, places where the density of matter is so low that an astronomer living in a hypothetical galaxy planted right at the center would face a truly terrifying night sky. Not because of what's there, but because of what isn't. No neighbors, no nearby galaxies, just absence. And now the real question, the one we've been circling around. What if our galaxy is in one of those places? To answer that, we need to go back to 1981. On the surface, an unremarkable year. But that year, an astronomer named Robert Kirshner, along with his team, was studying the distribution of galaxies in a specific region of the sky. And they found something that wasn't supposed to be there, or rather, something that simply wasn't there at all. A zone. An enormous zone in the direction of the constellation Boötes. And across a stretch of roughly 250 to 330 million light-years in diameter, there were almost no galaxies. A volume of space that should have held thousands, perhaps tens of thousands of galaxies, contained roughly 60. 60 galaxies in a space that statistics demanded should hold several tens of thousands. They called it the Boötes Void. The scientific community reacted the way scientists always do when something refuses to fit any existing model. They recalculated. They checked again. They recalculated once more. Because statistically, this void should not have existed. The models of cosmic structure formation at the time said that a region like this could not form so quickly, not within the current age of the universe. And yet, there it was. Now, at this point, you might be thinking, all right, a large void, that's striking. But we're not inside it. We're just distant observers looking at some cosmic oddity. Fair enough, hold on. In 2013, 3 astronomers, Keenan, Barger, and Cowie, published a study in the Astrophysical Journal. Dense, technical, full of mathematics. And for several years, their results passed almost without notice. What they did is simple in principle, even if the execution is breathtaking. They mapped the density of matter around us, not just around the Milky Way, but around us, within a radius of nearly 2 billion light years. 2 billion. To give you a sense of scale, light, traveling at 300,000 kilometers per second, would take 2 billion years to cross that distance. 2 billion years. The current age of the entire universe is roughly 13.8 billion years. What Keenan, Barger, and Cowie mapped was a region representing a significant fraction of the observable cosmos. And in that map, there is a hollow, a massive depression in density. Our local group of galaxies, the Milky Way, Andromeda, and roughly 50 smaller satellite galaxies, sits at the center of a region containing approximately 20% less matter than the cosmic average. 20% might sound modest, but at this scale, it represents a staggeringly large amount of missing matter. Millions of galaxies, billions of stars, simply not there, not where they should statistically be. And this void, this colossal structure they eventually named the KBC Void, after the initials of its 3 discoverers, extends in every direction around us for nearly 2 billion light years. We are inside it. We always have been. We just didn't know yet. Now I can already hear the objection. That's one study. Maybe they got it wrong. And that's not just a reasonable reaction. It's the correct scientific one. Except that since 2013, other studies have followed, and they haven't contradicted Keenan and his colleagues. They've confirmed, refined, and deepened the finding. In 2019, a research team pushed the analysis further still. Using galaxy catalogs of unprecedented precision, their conclusion was clear. Not only does the KBC Void exist, but its internal structure is consistent with what general relativity predicts for an underdense region. The galaxies inside this void are moving at speeds that match exactly the mathematical model of a place where local gravity is slightly weaker than average. Do you see what that means? The galaxies are moving the way they should move inside a void, not the way they move in a dense region. As if the space around us carries a different gravitational signature. I want to pause here for a moment, because I almost moved past something essential. Einstein's general relativity, the theory that describes gravity not as a force, but as a curvature of space-time, predicts that light passing through a void behaves differently from light passing through a dense region. When a photon enters a supervoid, it gains energy. When it exits, it loses some. In theory, these effects should cancel out. But here's where the universe decides to be strange. If the universe is undergoing accelerating expansion, and we know that it is, I'll come back to that, then voids grow larger over time. And so a photon crossing an expanding void exits with slightly less energy than it had going in. That leaves a trace, a cold trace, a faint temperature dip. This is called the integrated Sachs-Wolf effect. It is real, measurable physics. And when we look at the map of the cosmic microwave background, the ancient radiation left over from the early universe, observed by the WMAP and Planck satellites, we find exactly this. Regions that are slightly colder in the directions of large voids. The most famous cold patch on that map is called simply the cold spot. A temperature anomaly in the direction of the constellation Eridanus, colder than the surrounding average by 70 microkelvin, which, in the language of the cosmic microwave background, is a significant difference. Whether this is the signature of a void in the foreground or something even larger behind it is still being debated. But what is no longer in question is that structures of this kind exist. and that they leave fingerprints in the oldest light in the universe. Now, I want to talk about a problem. A problem cosmologists call, without any irony, the Hubble tension. And this is where the mathematics of our story takes a genuinely unsettling turn. Edwin Hubble, the astronomer, not the telescope, established in the 1920s that the universe is expanding. Galaxies are moving away from each other. The farther away a galaxy is, the faster it recedes. The rate of that expansion is called the Hubble constant, written as h0. For decades, measuring this constant was the holy grail of cosmology. Today, we can measure it very precisely. The problem is that we get two different values depending on which method we use. And those two values cannot be reconciled through measurement error. When we measure the Hubble constant using the cosmic microwave background, analyzed by the ESA's Planck satellite, we get approximately 67.4 kilometers per second per megaparsec. When we measure it using local objects, variable stars called Cepheids, and a specific type of stellar explosion called Type 1a supernovae, we get approximately 73.4, a difference of 6 units. That sounds small, but the margin of error in each measurement is now so tight that the two values barely overlap at all. The probability that this gap is due to chance is less than 1 in a million. In statistics, that's called a 5 sigma result. Beyond any reasonable coincidence, and cosmologists are facing a wall. Either the instruments are flawed, and James Webb has ruled that out, as we'll see in a moment, or the standard model of physics is incomplete. Or there is something in our local cosmic environment that is skewing our local measurements. You see where this is heading. In 2018, researchers Kenworthy and Barger published a study that made a lot of people uncomfortable. Their hypothesis: what if the KBC Void is responsible for the Hubble tension? Here is their reasoning, simplified. If we are in an underdense region, a region where local gravity is slightly weaker than average, then galaxies around us have a natural tendency to drift outward toward denser regions, toward the edges of the void. That outward flow of matter adds itself on top of the general expansion of the universe. This flow is called peculiar velocity, and it creates an illusion. When we measure the expansion of the universe by observing nearby objects, we are actually measuring the general expansion plus this additional outward flow. We overestimate the expansion. We measure a larger Hubble constant than reality actually gives us. And that locally measured value of 73.4? It corresponds precisely to what you would calculate if you applied the mathematical corrections for an underdense region of the size and shape of the KBC Void. That might not be a coincidence. Or maybe it is. And that's what I love about this story. We don't know yet with certainty. But the numbers line up in a deeply troubling way. At this point, you might ask, why didn't we notice this sooner? Why did decades of astronomy fail to detect something so enormous? The answer is almost poetic in its cruelty. Because we're inside it. Imagine a fish trying to map the water it lives in. It can detect variations, currents, warmer patches, colder zones. But the water itself, as a whole, is its world. It's its reference frame. It's its normal. We are in exactly the same position. From inside the void, the space around us appears broadly homogeneous, because our instruments were long too imprecise to detect a density depression this diffuse, spread across distances this staggering. It took galaxy catalogs of sufficient completeness and depth. It took the Sloan Digital Sky Survey, which mapped the positions of more than 1 million galaxies. It took the 2-micron All-Sky Survey, which mapped galaxy distribution in infrared across nearly the entire sky. It took supercomputers to process all of that. And when those tools were finally in place, the structure began to emerge. Slowly, like an image forming in a developing tray. Our void. But let's go further still. Because the KBC Void, impressive as it is, may only be the beginning. Just outside this void, at its edges, in the surrounding filaments, there are structures, superclusters of galaxies. Laniakea, our local supercluster, was discovered in 2014 by Tully and his team at the University of Hawaii. 500 million light-years across, 100,000 galaxies inside. And Laniakea itself sits at the edge of something even larger. The Perseus-Pisces supercluster and other massive concentrations of galaxies that form the walls and filaments of the cosmic web surrounding the KBC Void. These structures are the shores of our void. We can see them because they are brighter, denser, and more luminous than the emptiness within. And this asymmetry, the difference between the interior and the exterior, generates a flow, a galactic current. Astronomers have measured it. Our Milky Way is in motion. Not just carried along by the general expansion of the universe, but also moving toward a specific point in the sky known as the Great Attractor, a region in the direction of the constellation Centaurus, roughly 250 million light-years away. And that motion is mathematically consistent with what you would expect from a galaxy drifting out of an underdense region toward a denser one. Consistent with the KBC Void. I want to stop on that word, consistent, because this is where science is honest, and it's why I trust science. Consistent does not mean proven. It means the data doesn't contradict the hypothesis. The numbers line up, the model holds. But the universe is 13.8 billion years old. It is vast beyond comprehension. It has had time to build structures so complex and so interwoven that there may be other explanations we haven't yet considered. I don't want to hand you a certainty we don't have. What I want to show you is that the evidence is accumulating and that it converges on something very specific. In 2022, the James Webb Space Telescope, the successor to Hubble, launched at the very end of 2021, the most sensitive astronomical instrument ever built, began returning its first images. And almost immediately, cosmologists encountered a surprise, not a small one. A surprise that reignited every ongoing debate. Webb confirmed the Hubble tension. Its first measurements using Cepheid variable stars, the same type of stars used for local expansion measurements, returned the same result as Hubble, approximately 73.4, not 67.4, which meant one very simple thing. The gap between the two measurements was not caused by instrumental error. Hubble and Webb are two entirely different telescopes built with two entirely different technologies. Same result. There is genuinely something wrong with our understanding of the universe. And the KBC Void remains one of the very few hypotheses that can explain this discrepancy without requiring a complete rewrite of fundamental physics. Though that possibility can't be ruled out either. There is a major objection to this whole framework, and it would be dishonest to ignore it. The standard cosmological model, known as lambda CDM for cold dark matter with a cosmological constant, predicts how large structures in the universe form over time. It describes how voids, filaments, and clusters emerge across billions of years. And according to this model, a void the size of the KBC Void, with a density deficit of 20%, should be extremely rare. Statistically improbable. Not impossible, but improbable. Some simulations suggest that a structure like the KBC Void would appear in only a tiny fraction of regions in any simulated universe. If that's right, then either we were extraordinarily lucky to end up in this void, or lambda CDM is incomplete, or the measurements of the KBC Void are less accurate than claimed. 3 options. None of them comfortable. And this is exactly the place where modern physics finds itself stuck, with data that seems to say one thing and models that resist accepting it. There's an image I've had in my mind since the beginning of all this, and I think now is the right moment to share it. Imagine the universe as an ocean, a 3-dimensional ocean, infinite in every direction. Inside that ocean, there are waves, crests of matter forming the filaments and clusters, and troughs forming the voids. We are in a trough, a deep one, and the sea surrounding us, though it's everywhere around us, is not where we are. It is at the edges. It is in the directions that look empty to our eyes, but are in reality the shores of a continent of matter that the curvature of our void hides from us. And occasionally, when a photon of light from a distant galaxy crosses this trough to reach our telescopes, it carries with it a trace, a signature, a faint modification of its energy that says, "I traveled through a void. I traveled through your void." That is cosmic poetry encoded in differential equations. I can't talk about all of this without addressing dark energy, because it is at the heart of the mystery. We have known since 1998, thanks to the work of Saul Perlmutter, Brian Schmidt, and Adam Rees, work that earned them the Nobel Prize in Physics in 2011, that the expansion of the universe is not slowing down. It is accelerating. Something is pushing galaxies apart faster and faster. We called that something dark energy. According to current models, dark energy makes up 68% of everything in the universe, all its matter and energy combined. 68% that we simply do not understand. Ordinary matter, stars, planets, gas, you, me, accounts for roughly 5%. Dark matter, which we cannot see and detect only indirectly through its gravitational effects, accounts for roughly 27%. And this absolute mystery we call dark energy, 68%. Here is the connection that few people make instinctively. In supervoids like the KBC Void, dark energy dominates even more completely than in dense regions, because there isn't much else there. Not enough matter to counterbalance its push. In our void, dark energy operates almost without opposition. And that may be precisely why local measurements of expansion appear larger. Because we are measuring an expansion amplified by our position in a place where dark energy has nothing to hold it back. There's a detail that kept me awake one entire night, and I need to share it. The KBC Void has a radius of roughly 1 billion light years. To cross it at the speed of light would take 2 billion years. Twice the age of our sun. Now consider this. The photons that have traveled from the edges of this void to reach our telescopes left their sources between 500 million and 1 billion years ago. At that time on Earth, complex multicellular life was only just beginning its great explosion of diversity. The first marine animals barely existed. Dinosaurs wouldn't appear for another 250 million years. And that light was already traveling toward us. It was already crossing our void while the first fish were learning to swim, while dinosaurs ruled the land, while the first human civilizations were building their temples. And it arrived, just now, inside the instruments of our telescopes, to tell us, "You live in an empty place. There's another angle worth sitting with." Because so far we've talked mostly about density, matter, and galaxies. But there's an even more vertiginous dimension to all of this. The question of typicality. In cosmology, there's a guiding principle called the Copernican principle. The idea that we do not occupy a special position in the universe, that our location is statistically ordinary, typical. For a long time, this principle shaped all of cosmology. The universe is homogeneous and isotropic at large scales, the same in every direction, the same everywhere. Except, if we really are in a void like the KBC Void, we are not in a typical position. We are in a minority position, statistically rare. And that raises a question that borders on philosophical vertigo. Why are we here? Why did our galaxy form in a void rather than in a dense filament? Is it pure chance? Is there a physical explanation for why the Milky Way emerged in an underdense region? Did our cosmic environment influence our evolution, the emergence of life, of consciousness? These questions go beyond current physics, but they arise directly from this data, directly from this map, directly from these equations. There is a researcher I need to mention here because his work genuinely struck me. Lucas Lombreiser, a theoretical physicist at the University of Geneva. In 2020, he published a study in the journal Physics Letters B, and his conclusion was radical. Lombreiser proposed that the Hubble tension can be resolved if we assume we live in a region of the universe where the local value of the cosmological constant, what we call dark energy, is slightly different from its average value everywhere else. What if dark energy is not a single uniform universal constant, but something more like a field that fluctuates slightly from one location to another? And what if our void, by its very underdense nature, sits in a region where that field takes a slightly different value? If that's correct, then the laws of physics, or at least some of their parameters, are not exactly the same everywhere in the universe. There would be no single universal physics. There would be a local physics, shaped by the local cosmic environment. That is not a revision of cosmology. That is a revolution. I should be clear. It is one hypothesis among several. But it is being taken seriously by very serious people. And I can already hear the next question forming. Are there other voids like ours elsewhere in the universe? Yes, many. The Boötes void, already mentioned, 250 to 330 million light-years across. The Eridanus void, one of the largest supervoids known, in the direction of the constellation Eridanus, close to 1 billion light-years across by some estimates, though its exact size is still debated. The Sculptor void, the Taurus void. The universe is scattered with these empty regions. And some of them are so vast, so deeply empty, that if you lived in a hypothetical galaxy somewhere near their center, you would look up at a sky that is almost black. Almost no galaxies visible, even with the finest instruments imaginable. A sky without stars, without neighbors. A total cosmic silence. There's something that keeps coming back to me when I think about all of this. A detail that seems minor but says everything about our situation. The light from the nearest galaxies beyond the Milky Way, the galaxies of the local group, takes about 2.5 million years to reach us. 2.5 million years. And those galaxies are, cosmically speaking, our immediate neighbors. Now imagine being positioned at the center of a void the size of the KBC Void. The light from the first truly dense, truly populated regions, from the filaments surrounding the void, would take hundreds of millions of years to arrive. We would be surrounded by relative darkness, not complete darkness. Our sky would still contain galaxies, still show distant stars. But compared to a galaxy living inside a dense filament, our sky would be less populated, less luminous, more solitary. And perhaps that's also what our universe is. Not a cosmos teeming with nearby neighbors, but a profound cosmic solitude softened by the presence of roughly 50 small galaxies in our local group. Perhaps our intuitive sense of the universe's density has always been skewed by our position inside this void. I want to be completely honest with you. Not all scientists agree on the KBC Void. There are debates, criticisms, papers that challenge the results of Keenan, Barger, and Cowie. Some researchers believe the density deficit is real, but considerably smaller than 20%. Others argue that selection effects in the galaxy catalogs used could create a false impression of underdensity. And that's how it should be. That's science functioning as it's supposed to. But here's what's striking. Even the harshest critics acknowledge that we are in a region less dense than the cosmic average. The debate is about scale, not existence. The void is there. Its exact size, its precise degree of underdensity, its role in the Hubble tension, those questions are still open, still being investigated, still in flux. And honestly, that's exactly why I wanted to explore this. Not to hand you a finished truth, but to bring you to the precise place where science is wrestling with itself. The place where certainties begin to crack, and the truly important questions begin. In the months before writing this, a new study used preliminary data from the Dark Energy Spectroscopic Instrument installed at the Kitt Peak National Observatory in Arizona, a device capable of measuring the positions and velocities of tens of millions of galaxies with a precision never previously achieved. Its first analyses confirmed something essential. Dark energy may not be constant over time. It may have evolved. It may have been stronger in the past. And if it evolves through time, it may also vary through space. And if it varies through space, then our position inside the KBC Void takes on an even deeper meaning. Because we wouldn't just be in a place with less matter, we would be in a place where the fundamental rules of the cosmos are infinitesimally different. DAISY is mapping the universe with unprecedented precision. In the coming years, its data will either confirm or overturn hypotheses that today still feel speculative. We are at a turning point. Before I close, there's one final direction I want to take, because something has been sitting with me since the very beginning. There's a question no equation can yet answer, and that's the question of what this means for us. Not physically, but as conscious beings, as humanity. For centuries, we have tried to understand our place in the universe. Copernicus told us we are not at the center of the solar system. Hubble told us we are not at the center of the galaxy. Cosmologists told us we are not at the center of the universe. And now we are learning that we may be in a particularly empty corner of the cosmos, statistically marginal, not representative. Should that unsettle us? Perhaps. Or perhaps there's something extraordinary in this, because from this empty place, from this relative cosmic solitude, atoms assembled. They formed molecules, they formed cells, they formed brains. And those brains developed mathematics powerful enough to detect the very void in which they float. We are cosmic dust in a galactic void that has figured out it is cosmic dust in a galactic void. That, to my mind, is the true astonishment of this story. So where do we stand? The data from Keenan, Barger, and Cowie shows an underdense region with a radius of roughly 2 billion light-years around us. The Hubble tension, a gap of 6 units between 2 confirmed measurement methods, verified by James Webb, may be explained by our position inside this void. The velocity flows of surrounding galaxies are consistent with what general relativity predicts for an underdense region. The integrated Sachs-Wolf effect leaves traces in the cosmic microwave background that correspond to the presence of enormous voids. And the newest data from DESI suggests that dark energy may be neither uniform in time nor, perhaps, in space. All of this doesn't converge on a certainty. It converges on something more unsettling than a certainty, on a growing conviction that we have misunderstood our position in the universe. that we have built our models from a biased vantage point, and that the instruments now at our disposal, Webb, Planck, the forthcoming Rubin Observatory, the Euclid Space Telescope launched in 2023, may force us to revisit everything. Here is the final image I want to leave you with. Imagine you are looking at a map of the universe, a three-dimensional map where every point of light is a galaxy. You zoom in, you zoom further. You see the filaments, the walls, the clusters. And at the center of this map, there is a darker region, a less dense area, a hollow. You zoom in again and realize that inside this hollow, at a scale incomparably smaller, sits our supercluster, Laniakea. And within Laniakea, a group of galaxies. And within that group, the Milky Way. And within the Milky Way, a spiral arm. And within that arm, an ordinary star. And orbiting that star, a small blue planet. And on that planet, beings who looked up at the sky, invented mathematics, built telescopes, sent signals into space, and who have perhaps, for the very first time, understood what immensity of emptiness they are floating inside. The answer to the question, where are we in the universe, is changing. It may always have been changing. And it will probably change again. But what we already know, with growing mathematical certainty, is this. We are not in an ordinary place. We are in a void, an immense void, a void that has been shaping us without our knowledge. And somewhere in the equations that describe the curvature of this nearly empty space, there may be the key to one of the greatest open questions in all of cosmology. We haven't yet found the lock, but the numbers, all the numbers, are pointing in the same direction. Take a moment before we go any further. Look around you, your room, your living space.